Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome back to another episode of Machine Learning Made Simple. Today we are diving into something that could redefine AI as we know it, and that is called inference timescaling. It's a mouthful, but let me explain. For years, AI has followed one rule. Bigger is better, more data, more layers, more computational resources. But that approach has a problem. It is very expensive, it is slow and out of reach for most people. The biggest companies with billion-dollar budgets can train models like GPT-4 or Claude. But what about everyone else? What about the startups, the independent researchers, the businesses that want powerful AI at their disposal but don't have access to those massive supercomputing clusters? That's where this new paradigm comes in. Then this is called the inference time scaling, and it changes everything. Instead of making AI models larger, we are going to optimize them now at the moment they're used. Think of it like studying for an exam. You could try memorizing every single fact, or you could learn how to think critically and solve problems logically. The second approach obviously works better and it also scales better. If you learn how to think critically, then you can probably do better in multiple exams. Like maybe you do good on math, then you also do good on physics if you learn that skill. And that's what this new paradigm is doing. Researchers have found that by training models to reason better at inference time, which means when they're being prompted to give an answer, and then not during training time, even a tiny model like a 32 billion parameter model, which is a very small model, can match or even outperform a 640 billion parameter model. That's a 20 times larger model, and it's an order of magnitude improvement. It's not just an upgrade, it's a shift in how AI thinks. Like think about AI in a part of our daily lives. It's behind chatbots and customer care service chatbots, and everyone have used those customer care chatbots. They only work like 10% of the time. You have to pick up the phone and ask you to send over to a human service agent. Most of the times those service agents completely misunderstand the context, and that's because they are running a very fast lightweight model, AI model that sacrifices reasoning for speed. But with this new paradigm, the inference time scaling, the chatbots can think deeper and solve complex issues. And now with this new paradigm, the companies can deploy AI that can think deeper, reason better, and solve complex issues on the spot without running massive models in the background on the cloud. That means smarter AI, better customer service, and huge cost savings for businesses. And this isn't just about chatbots, like that's only one single use case. Think about self-driving cars. Right now they rely on huge cloud-based models to process the road conditions. But imagine a car that doesn't have to wait for cloud services. And you probably had heard of it that once there was a huge traffic jam in one big city, I think it was San Francisco, where all those self-driving cars came to a standstill because they lost connection to their cloud service provider. So if the cloud service provider fails or have a downtime, all those self-driving cars will stop in the middle of the traffic, and guess it's a nightmare. That's why we don't want to drive next to a self-driving car, because they can just stop whenever the service gets disrupted. That's not fun. So now if this new paradigm is implemented, they don't have to wait for the cloud servers. It can think on its own in real time. Inference time scaling allows those AI models to run effectively on the vehicle itself and react almost instantly to obstacles, changes in traffic, and unpredictable drivers. Or let's talk about banking. Every time you swipe your card or make a purchase online, an AI model is running in the background, checking for fraud. But during peak shopping hours, think Black Friday, holiday sales, these fraud detection models slow down. Why? Because they're processing millions of transactions per second, and the model's ability to detect fraud in real time is really limited by its size. But with this new paradigm of inference time scaling, the fraud detection models can dynamically adjust their reasoning power, because they'll be running on those edge devices. Like in the card swipe machine that you swipe, that's where they will be running, and they can catch fraudulent transactions almost instantly without any kind of cloud infrastructure. And that's where it gets even more interesting. AI isn't just getting smarter, it is getting cheaper. Right now, most advanced AI models require massive cloud infrastructure, and that's why companies like OpenAI and Google charge an arm and a leg for the access. It's very expensive, especially for many third world countries. Startups in third world countries are really struggling because of the massive cost for OpenAI models. But with this new paradigm of inference time scaling, it allows smaller open source models to achieve similar performance like those large closed source models, which means that startups, independent researchers, and resource constrained small businesses who couldn't really afford the AI now can have access to those world class intelligence. Now let's talk about why this actually works. One of the biggest discoveries in AI research is the models perform what they call thinking out aloud. Instead of jumping straight to an answer, they break problems into logical steps, like a student showing their work on a math exam. And this is called chain of thought reasoning. Here's what is happening. Closed source models like GPT-4 and Claude already do this, but they hide the reasoning process. DeepSeek took a different approach. You might have heard of DeepSeek. It's quite a popular topic in news media to talk about DeepSeek, and we covered this in a previous episode. But what is about in DeepSeek? So what is happening? Closed source models like GPT-4 and Claude, they hide their reasoning processes when they give answers. DeepSeek took a different approach. They made their models' answers processes visible. Researchers then realized that the longer an AI model thinks, the better are its answers. So instead of making the models bigger, the researchers realized they can just make the thinking process longer. In fact, this was probably already stumbled upon by OpenAI researchers, but they did not disclose it to the open research community. And that is where DeepSeek came in, and they revealed that they have noticed this kind of emergent behavior, which is known as the aha moment. In their paper, if you look at the paper, they discuss that there is an aha moment where they give the model a math problem to solve. The model starts solving the math problem, and then it goes down a wrong path, and then suddenly catches itself in the process and realizes it is making a mistake and going down a path which is not correct. So then it course corrects and goes to the right answer. So it has this aha moment, which the DeepSeek researchers published in their paper. And this is the first time people realized in the open source community and all the world that there is an emergent behavior that the larger models have, and there are ways to elicit that model. And then the researchers immediately realized that just by using this chain of thought paradigm, they can fine tune even a tiny model, and which can outperform a 20 times bigger model. And let that sink in. A model which is 20 times smaller, an open source model which is 20 times smaller than a closed source model, can outperform the closed source model and almost achieve nearly the same results, if not better. And this is why the research world is buzzing and the news media is also going crazy. Let's go beyond theory. This is already making an impact. Imagine you're a scientist and analyzing massive amounts of data in genomic data sets, and you're trying to identify new drug targets. Normally this process takes weeks because the AI models, and they are using AI models, and these AI models are struggling to reason through complex biological data effectively. But with this inference time scaling, an AI model can dynamically now with this new inference time scaling, an AI model can dynamically figure out how to allocate more reasoning power to the problem at hand, and that leads to faster discoveries and medical breakthroughs. Or take e-commerce, for example. Recommendation engines drive platforms like Amazon, Netflix, and Spotify. But what is the problem? When demand spikes, let's say during a major sale, or when there is a trending movie on when everyone is watching, and if you are familiar with the recent live event that Netflix hosted of the fight of boxing match of Mike Tyson, you'll realize there's substantial issues during the live stream. So that's when the models struggle to keep up, because they are not equipped to handle those kind of huge processing loads. So that's where the inference time scaling comes in. It allows AI to scale its reasoning dynamically, and it ensures better recommendation without needing massive infrastructure upgrades. And the changes are going to come even in gaming, because gaming uses those non-playing characters and you embeds AI in them. So the non-player characters in video games are notorious for being predictable. They repeat the same phrases, follow the same patterns. But now with AI that thinks dynamically, those NPCs can adapt a real-time reaction to players, learning from interaction and making virtual worlds feel more alive. Think about augmented reality games. People who get those immersive experience using those Meta's Oculus headgears, the virtual reality is simulated environments, those will get even more lively. The applications go on and on and on, especially in healthcare, cybersecurity, logistic, anywhere AI is used. The inference time scaling is going to make it smarter, faster, and more cost effective. And now for those who like diving a little deep on the technical side, here's a little of something which we will be covering next. We'll be covering the test time scaling and the inference time scaling, but more importantly, we'll talk about how the AI race is no longer about who can build the biggest model, it's about who can optimize their AI reasoning the best. So what is next? In today's episode, we're going to go deep. We're going to break down how test time scaling or the inference time scaling works step by step. Then we'll explore how researchers are preventing AI from gaming its own reasoning process. This is known as reward hacking. We'll talk about what are the measures they're taking to stop that process. We'll look at the cutting edge of AI optimization and where the research is heading next. So whether you're an AI engineer, a business leader looking to implement AI, or just someone who loves understanding where technology is headed, this episode is for you. AI is just about to get smarter, faster, and more efficient. Let's dive into how this inference time scaling is making that happen. This is machine learning made simple, and today we're not just talking about AI, we're talking about how AI is learning faster and is learning to think better. Let's get into it. One of the biggest challenges in advancing large language models is improving their reasoning ability without exponentially increasing the computational costs. Now, recent research has taken multiple approaches to this, and each has its own strengths and trade-offs. Before we go further and start discussing, going in depth into the different LLM reasoning processes that have emerged and all the different training processes that have emerged, let's do a quick survey. In 2025, we are seeing a major push to upgrade the reasoning capabilities of the large language models. The OpenAI models already have very good reasoning processes, and DeepSeek came out and challenged that status quo. And now we see a renewed research, open research, in improving the reasoning capabilities of large language models, or of the small large language model, not the massive models, but the smaller models that these researchers with limited resources can train. So we are again going towards efficiency, and DeepSeek did really do a great favor to the open source community and open research community, because they demonstrated that here is a model which can train much cheaply, and the researchers realized that they can achieve the similar level of reasoning capability as the closed source models like the OpenAI's GPT series and Anthropic's Claude series, and they realized they can actually do it now. So the main idea nowadays is to take a smaller model and elicit chain of thought responses and use those chain of thought responses to train it further and fine-tune it further to allow it to learn what chain of thought processes are actually leading to successful answers. So essentially it's like a feedback. It's like a teacher asking a student, okay, tell me how are you going to solve this math problem, x plus 3 equals 5, and the student goes forward and it's like, I'm going to subtract 3 from both sides, and yes, that's the right process. If the student says, I'm going to divide both sides by 3, and like teacher will say, no, that's not the right answer, that's not the right thought process. So essentially what researchers we are doing now is training the large language models to reason correctly. And there are multiple approaches that have been explored in recent months, and new ones are coming up, and we're going to look at a few of those just to give everyone a taste of what's out there. And the main topic is knowledge distillation. So there are a few ways we can achieve those enhanced reasoning capabilities of these new large or smaller large language models, and one of them is knowledge distillation, where we can elicit the chain of thought responses from a large model like OpenAI and distill their responses. By distilling, we mean like capture the responses and use it to fine-tune our smaller models. And this has been done earlier with other models, and in fact DeepSeek researchers were kind of blamed that they distilled the knowledge from the OpenAIs. But the bottom line is that distillation is here to stay. If a model is open to public can distill the models unless it is explicitly banned in the terms of use. Now, that being said, the researchers do use models which do allow distillation, knowledge distillation. In fact, if you look at the Llama documentation, or Llama 3.2 70 billion is a knowledge distilled version of the Llama 405 billion model. So they take the large model and let it learn as much and consume as much data as possible, and then use that knowledge to and distill it and to train a smaller model. And we're going to talk about the nuts and bolts of distillation in the future segment. So the discussion begins with this paper called Test Time Scaling, where researchers essentially used the chain of thought processes. So essentially use the outputs that DeepSeek provides, the chain of thought, captured that chain of thought, not the final answer, and use that to train a smaller model to elicit that kind of robust train of thought. So and then they manually tagged it. So some chain of thought, of course, are garbage. So they tagged them like they are not good. And then they took the chain of thoughts, which are really good, and used them to train and fine-tune this model, which turns out to be a very small 32 billion model, but can perform as good as a 641 billion model. In fact, we did cover this in the previous episode. So for the details, please go back to the earlier episode 62, and look at it and how we approached and broke down the whole reasoning process and how the training process, we broke everything down and made it very simple. But that was the simplest overview that we can provide, that essentially they distill the chain of thought, not the responses, and use that to create a training data set, which then they used to fine-tune a model. What does that mean? It essentially means that if someone is thinking aloud, let's say how to solve x plus 3 equals 5, we don't need the answer x equals 2. We need the intermediate steps. What should we subtract from both sides? 3. We should subtract 3 from both sides in x plus 3 equals 5. So that thought process is what is distilled. That thought process actually helps arrive at the right answers, because most of the complex problems that we're asking the large language models to solve requires multiple thinking steps, and those multiple thinking steps also needs training, and those training is not usually provided. The conventional machine learning training data set usually contains a question and answer. The question answer pair is what the LLM usually ingests. Now what we're doing is we're not just giving a question answer pair, but all those intermediate steps that allows any human being to arrive at the answer. Usually human beings do not say it aloud, or we do not publish those intermediate thoughts. Like if someone writes a paper or a research article, they don't go and write, okay, I went and searched Google for this. I looked up this article, I downloaded that journal piece, I did these things, I wrote a 50-word essay 3 years back, I used that. We don't provide all those thought processes. We just include them in the references and we're done with it. If we have to teach someone to follow that process, one way is to allow them to go through a grad school or in college where they learn these processes from their peers. That's the same process that we're learning the large language model now. What we really need is all the thought process and all those actions, the micro actions that we perform in order to perform our reasoning thought processes to arrive at a reasonable answer. So we are essentially distilling those actions, those thought processes, and training large language models to reason better. And the first one that really caught people's attention is this test time scaling, where they demonstrated that this can be done. In fact, OpenAI is probably doing it for a while now. It's just we don't know about it. Now, that being said, the moment this paper came out, everyone realized that this can be done. And then new research in different avenues came out. Many people realized we just don't need to do those extraction of the chain of thought and fine tune with that, make training data set out of that. We can explore other avenues, like we can do a Monte Carlo research. In fact, a paper came out, it's very technical, that's why we didn't cover it. So essentially we can do all of different methods. So we're going to explore a few of those methods today, and we're going to start with this specific method that is very simple. It's probably not simple to implement, but the concept is very simple. It builds on the idea of the test time scaling, of extracting the chain of thought and using it to fine tune a model. So let's talk about that quickly. So we are seeing different paradigms on how to improve the reasoning capacity of the large language model. So this new paper explored the chain of thought plus the distillation process. But before we can discuss that, let's discuss all the different structures and the frameworks that are in existence that can help improve the reasoning process. So we do a little brief overview before we go and discuss the latest developments. One of the biggest challenges in advancing the large language models is improving their reasoning ability without exponentially increasing the computational cost. Now, recent research has taken multiple approaches to this, and each has its own strengths and trade-offs. Let's break it down. First, we have the single long chain of thought reasoning. This approach trains the large language models to generate well-structured, step-by-step solutions. Essentially, they mimic how a human might work through a complex problem. Models like OpenAI's O1 model, the DeepSeek R1 model, they use this process to refine their reasoning through structured chain of thought responses. And they incorporate in-context reflection and sometimes even backtracking. So what is the benefit of this? So the ideas become more coherent and they have more logically structured outputs. But what is the downside? It requires significant training data and computational resources to make it all work. The reasoning steps themselves do not get trained during model training. The model has to come up with it. So they need to do those expensive reinforcement learning and all those fine-tuning to get those reasoning chain of thought processes incorporated. And OpenAI also does an agentic framework, so it's more cost intensive for them. So another approach is repeated sampling. Instead of training the model to generate a single perfect reasoning path, it will generate multiple responses for the same query. Think of it like taking multiple shots at the target. Some will miss, but some of them will go through. It's like the idea is that the best reasoning paths will be selected using a ranking method, sometimes called the best of n sampling. Like you take the best of the n and you sample them. Or it can also be a search guided technique like the Monte Carlo tree search. We don't want to get into Monte Carlo. Monte Carlo essentially means it's a probabilistic way of searching, right? We don't want to get into that, but it's deterministic sometimes and it can be probabilistic. So it has both. You have to turn on the dial to make it more deterministic. Now this method essentially increases the robustness by allowing the model to rethink problems multiple times. So as you can guess, it will be really slow, but it will be slow during inference time. So training time is not an issue. Inference time, it will be slightly slower. So the main cost is the increased computational overhead of generating the multiple outputs, and is definitely more expensive than producing just one. So essentially what OpenAI does is it takes this reasoning process, iteratively refining the reasoning process and puts it into the training. So what we're really doing is we are offloading the training time, computational complexity and costs to during inference time, which makes sense. Because if I have to release an open source model, I cannot put too much money into training it. I let the users spend a little bit extra to use that model and have those robust training steps and do it iteratively refine the responses. That method I will prefer. So then the cost gets offloaded from the open source large language model to the users who might be using it, and there's a little bit of cost sharing there. So that method really works for open source models. Then there is reinforcement learning. Of course, there is always a reinforcement learning method. This method optimizes the reasoning through iterative self-improvement, just like the previous method, but this is slightly different. And we're going to talk about that in more detail when we talk about the Tulu 3 and the DeepSeek R1, when they used a new process called the reinforcement learning with verifiable rewards. This is a new way of doing reinforcement learning, where essentially the model learns from the feedback and continuously refines the reasoning strategies. So this approach is excelling in the structured problem domains like mathematics and coding, and where the correctness has to be precisely evaluated. However, this reinforcement learning, as usual, comes with its own challenges. It's very computational demanding and highly dependent on the reward model, and that's the tricky part. Sometimes those rewards cannot be correctly defined, and that's a very, very tricky subject. And we are exploring that subject in our reinforcement learning series, which we are doing in parallel, in tandem. So it can get tricky to get this reinforcement learning with verifiable rewards right. And so we move forward with another approach, which is called a simple distillation approach. And you might have heard of it because the DeepSeek research team was accused of using distillation to distill away the knowledge from the OpenAI models, which I don't think was allowed under the terms of use. But I'm not sure. I'm not a legal scholar in the AI and machine learning world. So this distillation approach is surprisingly effective. Instead of training a model from scratch, This method essentially transfers the reasoning capabilities of a more powerful model. Think OpenGPT's GPT-4o or anything above a 1 trillion model, or even the 405 billion Llama model or 600 billion DeepSeek. So the researchers have taken models like the DeepSeek R1 and then distilled their reasoning into smaller parameter efficient versions using these techniques, and essentially it's a form of LoRa fine-tuning. And you might wonder, how small are those distilled models? They can be 32 billion in size, so they are very parameter efficient. That's where the word parameter efficient comes from, because a small number of parameter stores a lot of extra data. So this method is far more resource efficient than the traditional training and requires significantly less data. However, there is always a trade-off. The distilled models may lose some of the depth and flexibility in reasoning compared to those larger counterparts. So what's fascinating is that these approaches aren't mutually exclusive. In fact, if you ask me to build and large language model, enterprise grade large language model, I'll combine all of them. I'll leverage reinforcement learning to refine the knowledge, distillation to make it more efficient, and also repeated sampling to further boost reliability. And this I really like that. Those iterative refinement I'm a big fan of, because large language models have shown that they can iteratively improve their answer. You can try it yourself. You can ask ChatGPT a simple question, it will give a response. And you ask ChatGPT to evaluate it again and refine it and redo an updated version. Essentially ask ChatGPT to grade its own answer and revise it. You see, if it does it two or three times, the responses get substantially better, especially if you're writing essays. If you're writing a simple 500-word essay, the first response, the first draft that ChatGPT gives, and everyone knows this who uses ChatGPT, is not that great. So you have to iteratively refine it. Now, there is a faster way of doing it rather than copy and pasting and asking it to refine over and over again. You can write a simple prompt saying that you have written a draft. After writing the draft, evaluate on these metrics. For example, the metrics can be engagement, how engaging the article, how is the article, the number of hook words in the article, is it SEO optimized, and whether it has a good flow in the document, is it friendly enough, if it explains all technical words correctly. And you can have a few of your own metrics that you can pass on and ask, evaluate your draft based on these metrics. Whatever the score is, try to improve it. Do it 2 or 3 times till you reach a 9 out of 10 in each of these metrics. You can do that iteratively, and ChatGPT will automatically do that in the background. It probably won't even print those intermediate outputs, but the final result you will get, it will give you the final score 9 out of 10 for each of those metrics. And then you'll see that the final version would be substantially better than the first version that ChatGPT gives you. And this is the beauty of the iterative refinement that I'm talking about. In fact, every large language model should have these already inbuilt. So it's not really cost effective to build this refinement process in consumer facing models. However, for enterprise grade models, which are used by enterprises internally, they should definitely implement this, at least when there is cost is not a concern, but at least when accuracy is more important than the cost, especially if you're presenting those results directly or submitting the results directly as a part of a pipeline to leadership, then accuracy is more of a concern than the cost. So then that's the right use case to use the refined framework, where you iteratively refine the LLM responses. So now that we know the basic frameworks that exist in order to improve the reasoning capabilities of a large language model, so let's look at this new idea that have come out. This is not really a new idea. So what they're saying is that they evaluated this process, and looks like in evaluating this process, when they take those chain of thought responses and build a training data, if they tamper with the data, then it changes the accuracy. In fact, we do expect the accuracy to drop if we tamper with the data, but they realize that tampering with the structure causes more massive drops in accuracy than just tampering with individual words. And I think that's the gist of the paper, but there are a few other details that we'll talk about. So let's talk about what the main idea of the paper is. The paper is essentially saying, and the paper is called LLMs Can Easily Learn to Reason from Demonstration. Structure, not content, is what matters. So I think the answer is in the gist of the paper is in the title itself. So, but let's quickly give a brief overview what the paper is about. So what they're saying is that they can use only 17,000 samples. That's a very small sample size. It's still a DeepSeek R1 model, and use those 17,000 to fine tune a Cohen 32 billion model. It's a really small model. So they are essentially distilling a large model. So this is the approach they have chosen. So we talked about all the different frameworks, long chain, reinforcement learning with verified rewards, distillation. So these people, researchers, they chose the distillation process. So they distilled a DeepSeek R1 reasoning model and used their chain of thought of the DeepSeek, because everyone can see it, and use that to create a training data set, which then they used to fine-tune a 32 billion model, a really small model. So they're saying that their process is very parameter efficient because they're training a 32 billion model, and also data efficient because they only needed 17,000 training examples. And their main claim to fame is that this 32 billion model can reach the performance of the OpenAI's O1 preview model. I'm guessing they are using the older model, but O1 preview is pretty big and with very robust reasoning capabilities. So they're able to reach that with a 32 billion model. Can you imagine that a 32 billion model will easily fit in a consumer grade GPU? So a consumer can get a local large language model which is having the same capability as the OpenAI's top of the line GPT models. That's amazing. That's an amazing achievement. But how did they do it? So when they fine-tuned the model, they realized that the model has learned to reflect and revise the intermediate thoughts. So what they're saying that the model will start in a reasoning path, then suddenly stop, and then go to a different reasoning path by saying alternatively, wait, but they allow the model to think freely. This is in sharp contrast to the previous paper we discussed with the test time scaling, where they cut off the chain of thought after a certain limit. So they just let the model think freely, and they realize if they do supervised fine-tuning or even they use LoRa, the model shows those sentient capabilities where it starts reasoning and then quickly changes direction and when it finds a better path. Is this sentience? I would argue against it. And if it's still probabilistic, I think what is happening is that when it follows a certain path, the probability is decreasing over time, and the reasoning training process is actually training the model to capture that. It's training the model to capture that change in the probability structure. So the model has some probabilistic model that generates those responses in an autoregressive fashion. I think the reasoning process is forcing the model. It's also learning to pay attention to the responses itself it is generating. So not only just the knowledge it has and the query it has, it is now also paying attention to the responses it is generating. And when the probability starts dropping, as the model sees its responses grow and the probability drop, it realizes that it's not going in the right direction. Then it changes direction. So that's what I think is happening. It's not sentience, or it might be something mimicking sentience, but that's what I think is happening. It's the model has learned to capture and follow its own reasoning processes and pay attention to it. So that there must be some attention layers which are learning to pay attention to the outputs of the models itself. So we'll see. There might be more research on this and people might come up with better ideas. Large language models are getting really good at reasoning, but what allows this reasoning? It's the long chain of thought reasoning. Now, till now, the open research community couldn't see those long chain of thought reasoning because OpenAI usually hid that behind their thought process. It will say it's thinking, but it will never show the long chain of thought processes it goes through. Then the game changed when the DeepSeek research team deployed the DeepSeek R1 model, which started showing that long chain of thought. Then people realized that there is a long chain of thought processes that's going on in the background, which OpenAI and the other closed source models don't demonstrate. So now the main thrust of the research is where do we find those long chain of thought responses and how to elicit more long chain of thought responses, because people finally realize the longer the chain of thought responses, the longer that chain of thought a language model demonstrates, the better its reasoning capabilities are. So even if you take a small language model, it's a 32 billion model, but you can force it to think longer and longer, it will arrive at the right answer eventually, which is not surprising fact, because it will explore different possibilities and finally find the right answer. So now the new research direction is to how to elicit those long chain of thought reasoning. And one of the ways people have looked at is to do something known as test time scaling, where they elicit the responses by actually training or fine-tuning the large language model or a smaller large language model like a 32 billion model on those long chain of thought responses that they scrape from the larger models like DeepSeek or sometimes even OpenAI. They essentially distill those responses and use that. And it has been demonstrated by that now famous paper called S1 Test Time Scaling, with the researchers demonstrate that is possible. In fact, you can use that chain of thought response training on a very small 32 billion model and make the 32 billion model give responses which are comparable in quality to a 640 billion DeepSeek model. So that's what people are. So the real question is how to scale this long chain of thought. It means how to elicit longer responses. Most large language models today generate very short chain of thought, except the OpenAI's latest models. However, you don't get to see those chain of thought because they hide it very effectively, especially if you're using their web interface. The OpenAI's model really have mastered the long chain of thoughts, but it's very hard to see that unless you use their very expensive APIs. Now, this paper that we are discussing isn't just about the COT, the chain of thought reasoning, how it works. It's also mainly about scaling that chain of thought, how to dynamically increase using some kind of reinforcement learning method, how to reward the model, how to fine-tune the model to think longer and harder and arrive at the right answer. How can researchers train models to perform complex reasoning with extended chain of thoughts? One key finding is that supervised fine-tuning on chain of thought data. So essentially you take the chain of thought data by scraping those chain of thought responses from different large language models. They can be short, they can be long, but you scrape them and use that as your training data set. But if we train our model or supervise fine-tune our model using that training data set, then the chain of thought responses becomes much better, and even better on unseen tasks. Like these are called out of sample tasks, like tasks that they have never seen before. Like if you have Qwen math model, which is specifically trained on a data set with only math problems, it has not seen physics problems, it can still solve a few simple physics problems just by reasoning. One key finding is that supervised fine-tuning on chain of thought data can help the model generalize to chain of thought reasoning to even unseen tasks, and we're going to discuss this soon. But this is a big deal because until now the absence of this long form chain of thought training data has been a bottleneck, and these researchers are proposing new ways to solve it. In fact, they're claiming that they have solved it, and let's look at how they have solved this problem. So what the researchers really did, they took a training data set, initial training data set of 7,500 training samples of math data set, and this is hand curated, by the way, and then they augmented that with some data set which is scraped from the internet. So the hand curated data set they're calling the gold standard, and the scraped data set, which is from the web instruct, they are calling. Now they're going to use these data set to fine tune Qwen 2.57 billion math model, which is extremely fine-tuned on math problems. So they're assuming that if they can use this math large language model, purely math LLM, and actually can make it give reasonable responses from out of samples. Out of samples means problems which are not part of the math data set, problems which the model might not even have seen in its training data set. If it can do that, if it can make the large language model so fine-tuned that it can even reason outside and think outside the box. Like for example, someone who only knows mathematics, and now they started teaching physics as well, which is great. So they are training the model so that it can also talk simply about other things, that not just only about their specialization. They just don't want the model to be boxed into their boxes. So to that end, they said they're gonna distill a Llama 3.1 8 billion model. So Llama 3.1 is slightly older version than we have Llama 3.2 now, and 8 billion is a substantially smaller model. So that's fine. So these researchers are probably resource constrained. So they're showing the open research community that this can be done with smaller models. So they take this 8 billion model and they're going to elicit responses from this 8 billion model and going to capture those responses, and then they're going to use those responses to create a data set and then fine tune. So this is a long process. But why do this long process? The reason to do this long process is to get those chain of thought responses and then create a training data set out of that. So they're going to elicit this chain of thought responses from that and extract those. And so there are a couple of ways they're going to do that, and we're going to go into slight details on how they're doing it, because that's the main goal of the paper, how to create those long chain of thought responses, especially from the smaller models which do not do those long chain of thought responses. So before we get into how they actually do those long chain of thought responses, let's just quickly give a brief overview of what we're dealing with. So now we have two training data set. One training data set is completely hand curated, and one training data set is from WebInstruct, which is scraped from the internet like Reddit and open forums, and where people ask all those questions and answers. Like someone submits a bug report on GitHub and gets answers, and some people say, oh, I have the same bug, I tried this, didn't work, I tried that, didn't work, and then finally they converge on a solution. So look at that. So those entire chain of responses, if you collect them, that actually forms a correct response, and that actually shows a chain of thought, a collective chain of thought of the entire community who are working together to solve a problem, like fixing a bug on GitHub, for example. Let's say a software has a bug and everyone collectively solves that bug, and all the blind alleys that people go, and if you scrape that and feed that into a large language model, the large language models can see all the different ways and people think, and different ways solutions people try, and finally arrive at the right answer. So it can learn those reasoning process, and that's the whole point of using WebInstruct database, is to use those scraped forum discussions, which are like months, weeks, even months long, which have a collective wisdom. Now they're getting compressed into a single file and fed into LLM, which can reason. Now there is a problem. Now, since these are not hand annotated or hand curated, they are just scraped by the scraping agent. They are not very high quality, which means there are mistakes. Maybe people say random things and go off topic on forum discussions. So if people are discussing about a bug on Photoshop new version, then some people might go off topic and started talking about GIMP, like start using GIMP or something, give up Photoshop. Like some people might do that. So those are the off topic things that needs to be rejected, and for that they perform something known as rejection sampling. And there are few ways they have done the rejection sampling, and I think that's pretty smart the way they have done the rejection sampling. So the way they have done the rejection sampling is that they take the Llama model and they pass those discussions into the Llama model, and let's say the bug in Photoshop, let's say how do I fix this, right? And then it will come up with some answer, and then they compare the answer with this which they've seen in the forum results, and if they see a variance, then they'll pretty much reject those answers. So in fact, I'm going to just read it from the paper. They said to extract the short form answers, we first prompt the Llama model to extract from the raw responses, then apply rejection sampling with Qwen. So what does it mean? It means that they will pass on the question, let's say this is a bug, solve it, and get the raw response from Llama. And then if it doesn't match or not even close to the actual forum responses, then they'll reject both of them. So that's a way to do those rejection sampling. So that's where you improve the quality of your data set. So now let's talk about how they actually elicited that long chain of thought responses. Now, as we know that there is a long chain of thought and there is a short chain of thought. Smaller models do short chain of thought. Larger models like GPT-4 do long chain of thoughts, but we never usually see those long chain of thoughts. Now, there are a couple of other ways to get those long chain of thoughts. So they identified there are a few ways to achieve that. So one, they can distill those long chain of thought reasoning trajectories from existing very large long language models like GPT-4 with 1.2 trillion parameter models, which do provide those large chain of thought responses, or the DeepSeek 641 billion model, which also provides those really long chain of thought responses. They can distill those, which they have done. Or they said they can still take a small model and they can construct multiple trajectories and then slice and dice and add them. And let's elaborate on that. So they're essentially saying that since we cannot elicit really long chain of thought responses from the smaller models, why don't we make the model break down the task into smaller and smaller goals and sub goals, and then think about those goals and sub goals, and then have those chain of thoughts from each of those goals and sub goals, and then concatenate them into a very long chain of thought. This is, I think, a better way of doing it, because OpenGPT will have some chain of thought, but it will be small. But if we are using multiple agentic framework and creating all those goals and sub goals, breaking down the task and goals and sub goals, and each goals and sub goals have their own chain of thought, and we're concatenating everything, then it will create a massively long chain of thought. And I think that's the best way of creating that data set. In fact, that's, I think, is the heart of the paper, is to construct the long chain of thought, and that's where the main contribution is. So they go ahead and do it in a few ways, and let's talk about a few ways. We don't have to do it this way, but we'll just discuss their approach so that we get the idea of how it can be done. So their main idea is that first, let's clarify the problem, okay? Because that is itself a chain of thought, because sometimes we don't even understand the problems. People can say very ambiguous statement. For example, if someone says that see you at the bank at 3 p.m. What does that mean? Which bank? Are we going to the Chase Bank or the Bank of the River? So these are ambiguous statements that needs to be clarified. Another example of an ambiguous statement is, can you find me a match? Is that person looking for a love match or a matchstick? So these are ambiguous statements, and not that people will ask these ambiguous statements to an LLM, but the whole point is to clarify what the LLM is being asked. So if for example, I have done several times, it's like, explain this to me, or explain this architecture to me to LLM. So they was like, what explain what? Explain this architecture. I don't see an architecture. Do you mean the diagram you uploaded? It's like, we can even confuse ChatGPT several times. So it's important for the ChatGPT model. Now it's gotten better. I'm talking about the older model, the model 3.5, which used to get confused a lot if I was very terse with my explanation and prompts. So I learned to do very extensive prompting. Now that we learned that we should reduce our extensive prompting, because GPT-4 can pick up and reason better. So that being said, what it is doing in the background is doing this clarification step. What is the person asking? If you see the reasoning process that GPT somehow displays, it says, what is the person asking? What is the person trying me to do? Can I figure it out from the context? It actually performs those contextualized extraction of the question. For example, if I'm talking about an architecture diagram and I suddenly say evaluate this or score this, it's like, then you can see the thought process going, is the user asking me to evaluate this architecture diagram, or is this user asking me to evaluate our conversations or the last response? So it gets confused and then it self-corrects. So that's the clarification step that we can ask the model to perform before it proceeds. And then the next step would be to decompose the problem. So given the problem, decompose into goals and sub-goals and parts and sub-parts, and then solve them, each of them iteratively. Now, as you can see that each of these parts are very small problems that each can be handled by a smaller language model very conveniently with a short chain of thought prompting. And even if there is a very short chain of thought output, and that would be cumulatively grow larger and larger as there are more goals and sub-goals, each goals and sub-goals will have their own chain of thought reasoning from the large language model that will come out, and then as we keep adding them, it will start growing. And even if there are like 10 goals and sub-goals, and each of them had like 10 lines of chain of thought responses, easily we'll get 10 times 10, 100 lines of chain of thought responses. Like a large language model which can only generate 10 short sentences of chain of thought, we can now elicit and gather 100 lines of chain of thought just by that chaining process. Now we can also add a solution step, and it's like, hey, these are the reasoning steps and the goals and sub-goals that we have explored, and now combine all of them and find a solution. And also my favorite, reflection. Always add reflection, refine reflection. This step needs to be added at all times. The agent, the large language model, needs to reflect on its responses and see if it has made a mistake. In fact, ChatGPT, you can see it does it all the time. After it gives about to give a response, like, is that what I'm supposed to give? It's like, yes, verified, and then it gives a response. So as we can see that just by going through this process, breaking down the problem into multiple steps and sub-steps, we can already get a bunch of maybe 10 or 20 different steps, and each step, even if it has like 5 or 10 chain of thought responses, a combination, a concatenation of all those 5 or 10 sentences would immediately give us a very long 100 or 200 line chain of thought response. So that already creates a very high quality data set, and that is what these researchers have contributed. The rest of the papers just explores the different ways those length of the chain of thought can contribute to different idiosyncrasies of the large language model. In fact, they saw that if they increase the model size from 4 billion to 8 billion to 6 billion, the increased context length allows the longer and longer chain of thought process to be incorporated, and the model gets better fine-tuned. They did see a peak around the 8 billion model, and they realized that their chain of thoughts are not long enough to strongly elicit the responses from the 16 billion model. So what they said, that we just need longer chain of thought. So but this is a great find, that we finally realized that we can now increase the length of the chain of thought, and as we keep increasing the length of the chain of thought, the reasoning is also going to improve. So there is a high correlation. There is a scaling law there too. Previously, the scaling law people were interested in, it was the language model size. The more parameters you add to the model, the more training data set you add to the model, the better responses you get. But then we are hitting those resource limitations. Now we have like thousands of GPU farms whose only job is to train those large language models and consume massive amount of resources. So that is not really an option right now. We're looking at different scaling laws. We're just eliciting longer train of thoughts, we can improve the reasoning performances. Now, I would like to mention a very specific peculiarity of the training process that I find funny, because these models start to cheat at some point. And they do mention that they observe the cheating in the models. This is known as reward hacking. So when they are training a model or fine-tuning a model on a training data set, there are a few ways that can be done. Of course, there is supervised fine-tuning, which is you just give the training model and let the model do a stochastic gradient descent on this newly seen data set. So that's supervised fine-tuning. But then you can also add a reinforcement learning component to it, where you pick specific characteristic which you want to enhance, and you reward the model for eliciting that characteristic. In this case, the characteristic is the long chain of thought. The longer the chain of thought, you reward the model more, and if the shorter the chain of thought, you punish it. So now they realize that if they do that like that fashion, then the model will collapse pretty fast. So they found a smarter way of doing it. Sometimes model goes in the wrong direction. Like people go into the wrong direction, eventually they'll course correct. When the model goes in the wrong direction, if the model keeps thinking more and more, and slowly it tries to find its way back towards the right answer, then they punish the model less. And that's the beauty of the reward system that they generated. This is not a new system. This is an old system. This is called a cosine reward function, where the model gets increasingly less punished if they respond with longer and longer responses, because the idea is that if they think longer and longer, eventually they'll come up with the right answer. Even if they don't come up with the right answer, just by thinking longer or reasoning longer, you reward the model, punishing them less. If the model only thought for less than 1 or 2 sentences and got the wrong answer, then the model didn't put much effort. Then you punish the model with the maximum sentence, which is -8, for example, -8 reward. Like it's a punishment. Negative is punishment, positive is a reward, positive reward. Now, if the model thinks a bit longer, let's say 10 sentences, but still gets the wrong results, you punish it a little less, maybe -6 reward. If the model thinks 20 for 20 sentences and it still didn't arrive at the right result, then you punish it even less, maybe -4 or -3 reward, okay, or negative reward, -3 punishment. Now, if the model arrives at the right answer and truncates its responses quickly, then you reward it as proportional. Going to the other side, there is now a possibility of reward hacking. Now, if the model notices that it is getting rewarded for thinking longer, even if it has stumbled upon the right answer after the first chain of thought, like a first sentence of chain of thought, it will keep thinking, right? If it arrives at the right answer, it's like, let's say x plus 3 equals 7. What is the value for x? Subtract 3 from both sides. That would be the first chain of thought. And the next chain of thought might be the answer is 7 minus 3 equals 4. If it arrives at 4, then it might suddenly realize that it's going to get rewarded for thinking more. So it's going to think more. It's like, wait, it will start thinking. It's like, wait, I got the answer 4, but is that right? Let me verify. Then it will go through it again. It will loop over and over and over again till it accumulates a lot of rewards. So you have to shape the reward. This is known as reward hacking from the model side, and making sure that doesn't happen is known as reward shaping. And this is pioneered by Andrew Ng, whose course everyone knows. So the reward shaping is that you shape the reward that this reward hacking behavior doesn't happen. And how do we do that? We actually penalize for longer answers which are correct. Well, it is counterintuitive, but it works. For example, if a model arrives at the right answer after 2 sentences of correct thinking, then we reward it, let's say, +4. But if it takes 6 sentences to arrive at the right answer, then we don't give it +4, we give it +3. If it takes 20 sentences to arrive at the right answer, then reward is even less. So it is now getting penalized for thinking longer and arriving at the, so that prevents that reward hacking where the model will keep thinking over and over to even after it got the right answer. So this was initially observed in this boat racing game, that the researchers were trying to train an RL agent to do boat racing, and then they had these buoys that they have to cross and then turn around and come back. So one agent, they realized, figured out there is a peculiar strategy, because you have to reward the model to move forward, otherwise it will not move at all. It figured out that at buoy, when they turn, they get a reward. So they figured out a buoy and they went in circles around the buoy to gathering rewards. So the other boat, which was following rules and going towards the finish line, essentially ended up losing to the reward hacking agents, which is just doing loops around the buoy. I mean, it's brilliant. You have to give it to them. They figured out a loophole in the system, but that's the problem of reward system, because if the reward is not created correctly, then that reward could be exploited. And we have seen that those examples in society. Many people find those loopholes and exploit them till they are closed, and people are still doing it in real estate. Some people just buy real estate just to get the depreciation deduction on their income and totally write them off, because they are still don't intend to manage the business at all, but they do that. So that's one, but the loophole is never closed and probably will never be, because that's there to incentivize, and some people exploiting that loophole is not going to put a dent in the taxation system. So that's what these researchers observed. The model started reward hacking. The researchers found out a peculiar way of identifying if the model is performing reward hacking. They started looking for the aha phrases, and you probably have seen that paper which pioneered this, that they found that the model, when in DeepSeek, when they started reasoning, at some point they has like, aha, we have found an alternative path, and they started reasoning along that path, and that's called an aha moment. And there are multiple ways the reasoning and the chain of thought will have aha moment. That's a fork in their thought process. They're going down the wrong path, they had an aha moment, and they go on a different path. And there are a few words that come up in those aha moments when the fork in the road is taken. And one of those is that alternatively, well, let's think or wait for a second, or hold on, actually let me rethink that. And these phrases are used by the reasoning model when they're about to change gear and go in a different path and start thinking differently. And all we have to do is count these phrases, how many times they appear, to see if the reward hacking is happening. If they happen way too many times, let's say chain of thought is 20 lines long and these aha phrases are happening 20 times, pretty much reward hacking is happening. So the model is cheating the system. So that's how you know. And that's a beautiful way to figure out that kind of reward hacking is going on. It's a pure detective work and very well written paper. There's one thing the paper also mentions, that they also distill the knowledge from the Qwen model. We're not going to talk about distillation today. That's a topic for a completely separate episode, and it will take a long exposure to it. So, but we'll just say that some of those models can be distilled. So for example, the DeepSeek model is accused that they have distilled the OpenAI's chain of thought responses to have their own chain of thought responses. So people are going to do that. So people are going to just distill chain of thought from large models and going to train and fine tune their smaller models. That's the direction we're going right now. And distillation is something we're going to address in a future episode. So let's quickly talk about this new paper that came out. It's a technical report on a new model, and this is China's answers to the OpenAI's O1 series, the top of the line series models. This is called Kimi K1.5, and it is developed by Moonshot AI. Moonshot AI runs a models service similar to OpenAI's ChatGPT, meaning users can chat with their own models. But here's the big claim. They're claiming that they are outperforming OpenAI's O1 models in reasoning benchmarks, and they're not shy about it. The very first graph in the paper is a direct comparison showing where they win. Now, OpenAI's O1 models come in different flavors. There is O1 model and there is an O1 mini model. The O1 mini model is not multimodal. It doesn't handle vision or transcription. Kimi K1.5 also has both multimodal and non-multimodal version, so they make sure they be fair and compare their non-multimodal models against the OpenAI's non-multimodal model, which is the O1 mini, just for a fair matchup. Even with their reasoning still came out substantially better. And the key innovation is that their main contribution is just not about performance. It's about long context scaling during the reinforcement learning, which provides that post-training alignment of the large language model. Every large language model goes through this. It goes through a training, it goes through a fine-tuning and alignment post-training. So after the model training, it also goes through human alignment, human values alignment. And this is the last step of the reinforcement learning, which helps models generate responses that align with human values. But now reward models don't just judge answers, they reward long step-by-step reasoning instead of short responses. And that's what they're talking about. It's like, instead of doing those just human value alignment, why don't we upgrade that and also reward the models to think longer? Here's why that matters. If a model follows a chain of thought, it sometimes hits an aha moment. It starts down one path, it realizes it's wrong, and then corrects itself in real time. And that has been observed in earlier work like DeepSeek's paper on inference time scaling. And now we are seeing it applied here. So Moonshot AI took this idea and scaled it even further. They extended the context length during the reinforcement learning fine-tuning, meaning the model doesn't just reason better, it also remembers and processes more information at once. They tested two approaches. They use the classical reward modeling, which is the standard method of essentially doing this post-processing or the post-training of the model. And then they also did the chain of thought reward modeling, which is the newest iteration that people are using. I am guessing that they initially started with their classical reward modeling and they realized it's not performing very well. And when they switched, they saw an accuracy jump with the model. And in this chain of thought reward modeling, they elicit the model to think longer and longer responses, chain of thoughts, and they realize that the accuracy is substantially better. In fact, their accuracy jumped from 84.4% to 98.5% just by using that long chain of thought reward modeling. And that's a huge jump, almost a 15% improvement and almost close to 100% accuracy. And who would not want that? So I think they switch gears and completely switch to this chain of thought reward modeling. I think they're going to publish their paper or publish their model using the classical reward modeling, and then they saw DeepSeek results and people are going towards the long chain of thought process, reasoning, fine-tuning, and they immediately incorporated it. And they are quite agile, I'll say that. So behind the scenes, what is happening? They're using Megatron and VLLM, and if you're familiar with that, these are essentially model serving platforms. So if you have a model which is already trained, then you can serve them using these paradigms. Megatron can handle training, it can optimize large scale parameter updates. We don't need to know all that, but the basic idea is that they have to train in order to fine tune their large language model. So they have to do inferencing and training at the same time. So you get the idea. It's a very complex technological problem. Is a hardware problem as well. Think about it. If we have to train a reinforcement learning model by its own responses, it's not using some else's responses, as we said in previous papers, where they do data set curation by extracting the long chain long chain of thought responses and curate that to create a data set, and from that data set they fine tune the model. But however, these engineers, they realize, why don't we do it together? Why don't we use our own model to generate those long chain of thought responses, and then at the same time, while those chain of thought responses are being generated, then we use another training module which can extract it and train our fine-tune our model live while the inference is going in, like in tandem. That's a brilliant idea. It's engineering marvel and also very hard to implement, I'm guessing. But the good news and bad news. The good news is that they have released their architecture to the open source community. The bad news is that now people outside the United States are extremely capable in this, and we know that they're extremely capable in this hardware engineering and how they're able to fine-tune the model at the highest level. They're almost at par with OpenAI researchers. And so let's talk about the training infrastructure. So they are inferencing. While they're inferencing, they're taking the inferencing to fine tune the model. So that essentially creates a feedback loop. They train a model, they use it to generate long chain of thought responses, and then they fine tune the same model with its own improved responses. So this way they're essentially using their own AI to improve itself. This is a pretty interesting self-reinforcing system. So now let's talk about they also talk about the short and long chain of thought responses, and they realized that the longer chain of thought performed much better, which makes sense because more structured reasoning leads to higher accuracy if the problem is more complex. And then they ran some ablation studies, which is essentially tweaking the parameters to see what worked best. I'm not going to talk about that, but this paper is not just about beating the OpenAI's O1 models, it's about pushing the frontier of reinforcement learning. If you're interested, go and look at the paper. They have a table where they compare O1 Mini with their non-multimodal model and then O1 model, which is the largest, OpenAI's largest flagship model with full multimodality, with their own flagship model, the Kimi version K1.5, and they found that their model performs substantially better. Now that's kind of subjective because they used some open source evaluation framework, and usually people know that if you use those open source benchmarks which are kind of automated, the results slightly differ from human feedback. It is yet to be seen which ones human beings actually prefer more, is O1 model or this Kimi model, but it's yet to be seen, and we'll just stop here and we'll let people decide which one is better. But for now, I'll just caution against using it because you will have to enter all the data in a model that is served and hosted in a different country with their own terms and conditions and data usage regulations. So your data will be out there and you have to be careful about that. Definitely don't use for an enterprise grade application. That is it for today. Thanks for listening. We'll talk to you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.